Class. So I'm going to go ahead and record the lecture again. I got a few people said that was positive feedback, so just so you know, your voice will be forever recorded to uploaded to YouTube. So, with the test giving back, generally speaking, the first test, the class average was 39. Now the class average is 59. So the class average went up a significant amount. So actually, also the standard deviation got broader. So it just means that it's actually a broader distribution now. Before it was really narrow. But anyway, so the main feedback I got was the unlimited time was the better factor. So that's what you guys. Is there anything else? Anything that was better in the TLC than here?
I like being shut off from everyone, I guess.
Okay. If you want, you can take the test in the Learning Center if you want. You don't have to take them here. So, but we can talk about that later.
Yeah.
So, but let's see here. So it's the Wednesday after spring break is the next test. I can come in whenever the next class is over. It's around 2, maybe it's 1:30. But we can start early, and we can go as late as you want, really. Would that be better? Start early and end later. It's also not a lab day. Yes. So, or is it you guys wouldn't come at 2? You would just come at 3 and stay late? What's that? Okay. I will come early. Okay, I can do both. Do it all. Okay, sure. Yeah, okay. We'll arrange that. I'll figure that out after spring break and when the best time. And the thing is, there's organic chemistry is after this, so then we can go to the Astro Lab, but the Astro Lab starts again at 6 p.m. So we might only have like an hour in the Astro Lab. But then by then the library, the STEM library will probably clear out. But it depends on how much you want to move around. But I can find spaces for you. If there's only 1 or 2, I can stick you in my office. So, okay, is there any other suggestions about that, about how to improve the testing? You can always send me or the peer mentor an email. So if you want to be anonymous, you can email Calais and she can tell me. So if you don't want to be known. So, okay. So anybody have any questions about anything before we start? No. Okay. So we're talking about equilibrium, and we went into acid and bases, and then we talked about the buffers, and then we went into titration curves. I finally understood your question that you had about the reaction order, and because you were talking about the graphing with the natural log. No, it's not that. It's like what is he talking about? I'm like, oh, it dawned on me. Yeah, but the answer is still no. But, okay. So, now we're going to move on to things that are not acids and bases. And talking about solubility, we're going to talk about solubility, and eventually we're going to talk about complex formation. So, right now we're going to talk about the KSP, also known as the solubility product constant. So, has anyone ever been to caves before, like in the mainland, the big limestone caves, and seen stalactites and stalagmites? Have you seen that? Okay, not so many people. Yeah. Oh, okay. Yeah.
I hated it.
Yeah. So calcium carbonate, limestone marble is calcium carbonate. It's ever so slightly soluble, meaning a little tiny bit can dissolve. Not very much in water. And what happens is as rainwater comes down, rainwater is typically a little acidic. Not acid rain has a pH of 5.6. 5.6 is not acid rain. Lower than 5.6 is considered acid rain. Either way, that also aids in dissolving calcium carbonate. But anyway, calcium carbonate will dissolve a little bit, and then when the water drips down to stalactite to stalagmite, well, I guess dripping down. So tight something. I forget which one. Do you know which one's on the ceiling, which one's on the floor? I don't know. I want to say, okay. Well, the one that drifts down from the ceiling, as the water is coming down, some of the water will evaporate, and then the calcium carbonate will precipitate down, and then over many, many years will grow. So there are things, even we consider that to be insoluble, can dissolve ever so slightly in water. An example of that is fluorite. So fluorite, calcium fluoride. So calcium fluoride dissolving in water would be like this equation here. Calcium fluoride fluorite can dissolve to calcium plus 2 ions and then 2 fluoride anions. And it's just like the same old equilibrium. Products would be calcium fluoride squared because there's a 2 all over the concentration of calcium fluoride. But since calcium fluoride is a solid, it is not included in the equilibrium. So then the equilibrium, like I said, the equilibrium constant there, since solids are not included, KSB solubility product constant are just the ions. So let's use this to calculate something. So what is the molar solubility of lead chloride? And the solubility product constant for lead chloride is 1.17 times 10 to the minus 5. You'll be given all of the KSBs, or you'll be given the molar solubility if you have to calculate the KSB. So this won't be an undefined problem. So same old thing, initial change equilibrium. So initially lead and chloride are 0. Change, my S's look like 5s. So I always say, I put a $. You can use an S, but the thing is my 5 and my S look a lot alike. So that's just me so that you can tell the difference. And the equilibrium is going to be then solubility to solubility. So KSP is lead plus 2 ions, chloride anions. This is equal to, and don't forget to square it. So don't forget to square the inside. That's one of the common mistakes. So 1.17 times 10 to the minus 5 equals 4 solubility cubed. Then divide both sides by 4. Divide by 4 and then cube root it. So 1.17 times 10 to the minus 5 all over 4. Solubility cubed. And then cube root it to get rid of that. Are you guys following so far? Yeah, question? Was there? Oh, do you have a question or? Nope. Nope. Okay. One more. So put in the calculator 0.0143. So which means that that if you have a liter of water, that 0.0143 moles of lead chloride will dissolve in water, which is not a whole lot. But there's many things this is actually on the fairly soluble end of insolubility. Does anybody want the calculator? Raise your hand if you want the calculator picture up. Okay, you're good without the calculator. Okay. All right, so recap of this question. So the same old equilibrium, the initial change equilibrium ice chart, start with 0, and we shift right. So instead of using X, we're using solubility. You can use X if you want, but I just use I'll use a $sign because my S's look like 5s. So 1 extensive reaction for lead, 2 for chloride because there's a 2 in the equation, and that means, and look at the KSP value, it's lead ion plus or I'm sorry, lead ion times chloride anion squared. So don't forget to square the inside, and we get 4 solubility cubed, set that equal to the KSB, and get the solubility to be 0.0143 moles per liter. I should say, well, I guess molar, I'll put molar in there. Okay, questions now? All right, so let's do the other way around. What is the molar solubility? Oh, the molar solubility of silver sulfate in pure water is 1.2 times 10⁻⁵ molar. What is a KSP? You don't necessarily need an ice chart here. So, well, if you're just so used to doing this, this is the way you would do it. 0, 0 plus 2 solubility plus solubility, 2 solubility, solubility. The KSP is going to be silver ion squared, sulfate anion just as is. Plug it in. This is going to be the same. 2s squared. Solubility is 4 solubility cubed. But you know the molar solubility here. And you can take this number and put it in there. Equals 4 times 1.2 times 10⁻⁵ cubed. Same idea. So this is going to be 6.9 times 10⁻⁵. So solubility product constant like that. Okay, recap for this one, same idea, except we're given the molar solubility and we're asked to find the KSP. So if you like just using the ice chart, you can keep on going that way. Or if you want, you can skip all these steps. You can go from right here just to right there if you want. You don't have to go through that, but I've kind of trained you to do it this way, so that's why I'm kind of sticking with the same old procedure. But find out that the solubility product constant, KSP, is equal to 4 solubility cubed. You're given solubility, so just put 4 solubility cubed, and we get 6.9 times 10⁻⁵ for KSP. So, questions with this one? No questions? Some of your faces look kind of worried. Are you following? What? Molar solubility, that's how much will dissolve. So, which means for silver sulfate, so molar solubility of silver sulfate in pure water is 1.2 times 10⁻⁵ molar, which means I can get 1.2 times 10⁻⁵ molar of silver sulfate to dissolve in water. It's a very small amount. Right, that's not a very. That's 0.000012 moles. That's nothing per liter. Is that making sense? Okay. Other questions? Okay. So common ion. So we've done this before with acids and bases. What is the molar solubility of calcium fluoride and 0.1 molar sodium fluoride? So solubility is 1.46 times 10⁻⁻10. Okay, so with this one here, initially we still have 0. So same idea, write out the equation. Calcium fluoride breaks apart into calcium plus 2 fluorides. Initially, we have 0 calcium, but the difference here is we have 0.1 molar fluoride. So you see that it's in the initial. So change, we still have a shift right, equilibrium, oh wait, no, it's not 0. It's going to be solubility 0.1 plus 2 solubilities here. So is everyone okay that this 0.1, that the initial here for fluoride is 0.1? It's because of the 0.1 molar sodium fluoride. And sodium's a spectator, sodium's not involved in here. So it's a fluoride is common. Sodium is not common. Fluoride isn't common. That's why we care about the fluoride. And the sodium doesn't matter because it's not included in the equilibrium. So is everyone okay with this step? And we shift right, and then we just add them together. Okay. So you're good with that. And our KSP is going to be calcium plus 2, fluoride squared, and which also 1.46 times 10 minus 10 equals solubility 0.1 plus 2 solubility squared. You know what's nice about this, though? You could do the old look at things, and the 0.1 plus 2 solubility, the 2 solubility is not going to change 0.1 by that much. So we can approximate this to be solubility 0.1 squared. We can discount that solubility. And then, so let's see here. So 0.1 squared is 0.01 divided by that. Same thing as multiplying by 100. 1.46 times 10 to the minus 8 equals the molar solubility. You can disregard this one here because 0.1 plus 2 solubilities is going to be about 0.1. Do you remember we were talking about that in the last chapter? Well, I guess it has 2 chapters, right? If there's something that if the addition or subtraction of another term and it's going to be insignificant, you can just drop the term. You could solve this. That would be a cubic. That would be difficult. I'm not really good at solving cubics by hand unless it's something that's easy to root out. I can do it with a graphing calculator. But okay, well, recap. So we have solubility product constants, and we want to know what is the solubility now of calcium fluoride, except it's in 0.1 molar sodium fluoride. And the difference here is the initial has a common ion, so I have to include the common ion, go through the equilibrium of that KSV, calcium fluoride squared. One of the most common mistakes is forgetting to square things, especially squaring it in the middle. So solubility for calcium, 0.1 plus 2 solubilities for fluoride. We can discount the 2 solubility in the fluoride anion because 0.1 is much bigger than the solubility, and then just solve it straight away. So 1.46 times 10 to the minus 8 molar for the solubility. So questions with that one? Nope. Okay. So you can figure this one out. What is the solubility of calcium fluoride in 0.25 molar calcium nitrate? So all nitrates are soluble, so calcium nitrate's soluble. Calcium fluoride is not that soluble. So let's see if you can solve this one. Oh, you can't see this?
Didn't sign get squared because of the 2 in the reaction? That's the reason. Like a 2s would be squared.
The fluoride is squared.
Because of the 2.
Yes. Is anyone getting stuck? Raise your hand. So we think A, it's the square root of KSB divided by 2. We think B, square root KSB. How many think it's 2 times square root of KSB? We think it's 4 times square root of KSB. You guys too fast?
I think I didn't get that answer, but
Wait, we're not there yet.
Okay, more time. All right. Do you want the actual number? I can give it to you. It's 1.46 times 10 to the minus 10.
oh. Wait.
But I mean, you don't need it for this. This can be done without a calculator. Is anyone getting stuck? Honest.
Can you disregard the term?
Yes.
Okay, that's probably
Probably.
B. I don't know, it doesn't make sense.
What do you mean it doesn't make sense?
It
Makes perfect sense.
Disregarding the term on one side, but not the other. They're both S.
So,
This is weird.
I have confusion.
Because it's
So if let's say I go to Las Vegas and I make $1,000 playing blackjack, that's amazing. I'm like, I've made so much money, my life is going to improve so much. What's going to happen if Donald Trump goes to Vegas and makes $1,000? What if Bill Gates goes?
That's good.
Yeah, it's nothing to them. So, like, why didn't you tell your friends you just won $1,000 playing cards? You're like, meh. Well, Trump probably would. He'd probably tweet it.
Small.
Yeah, it's just, when you got billions of dollars, $1,000, that's like, that's at least 6 orders of magnitude. maybe 7, right? You don't care about it. So that's the same thing with the quarter molar the solubility there. It's not going to matter to calcium. Calcium doesn't care. So, but fluoride on the other hand, he's like a poor college student. How many ramen noodles you can buy with $1,000? Mm. So that's why it matters. That's why some matters to some, but not the others.
Same answer.
It would be about the same. For
I mean, I disregarded it. Like, I'm just at my final answer, and it still was the same answer if I disregarded it there.
See, that's what I'm wondering.
what?
Because like the whole time, like, what do you want? So you really,
Dang, I was thinking you distribute the 0.25 into 4.
Well, you can. When you distribute 0.25 into 4, you get 1.
That's great.
Well, I guess it's actually not. It's cumulative property, I think. If you want to be technical. Although there's only one term, so it would just be straight multiplication. So questions on this one? Are you guys following it? Okay. All right. So, general statement. In general, the solubility of an ionic compound with a strongly basic or weakly basic anions increases with increasing acidity or decreasing the pH. So, why is that? It is because of the equilibrium. So it's Le Chatelier's principle. So let me show you an example of that. So barium fluoride. So barium fluoride here. So barium fluoride solid. This breaks apart into barium plus 2 ions and 2 fluoride anions. Okay, so the question here will barium plus 2 or fluoride minus react with acid? And the answer is yes. Fluoride will react to make hydrofluoric acid. So remember, weak acids are clingy. Remember, we studied that before. Weak acids like to stay together. They don't like to split up. Okay, so strong acids and strong bases, they just fly apart. They're the friends. Like, you ever go to a party and your friend's like, oh, thanks for the ride, and they just disappear. And they may or may not even come home with you. Right? You're like, oh, thanks for the ride, see you later, bye. And weak acids are more like the clingy couple. Okay, you come to a party and they're always next to each other, they're always holding hands, they're walking around together. So maybe one leaves to go to the bathroom or goes outside to smoke a cigarette or something like that. But other than that, they're always together. That's a weak acid. And a weak acid, the strong acids, they are HCl, HBr, that's H there, HI, HNO3, HClO4, H2SO4. So, and sulfuric is kind of a weird case because it's the first hydrogen is strong and the second one is weak. So, which means that if you see chloride, bromide, iodide, nitrate, perchlorate, and bisulfate, those will not react with hydrogen. Everything else will. Everything else will. So that's an easy way to think of it. Everything else will. So in this case, if you stick barium fluoride into water, into acid, what happens is, so sticking into acid will cause the concentration of fluoride to go down, because the acid will react with the fluoride to form HF, and that goes down, which will cause it to shift right, and more barium fluoride will dissolve. So multiple steps here. So this is the equilibrium for barium fluoride. Barium fluoride, 1 part barium, 2 part fluorides. And you stick in an acid, what happens? The acid will not react with barium, it will react with fluoride. Why? Because fluoride is the conjugate base of a weak acid. It's a weak acid because it's not a chloride, bromide, iodide, nitrate, perchlorate, or bisulfate. HSO4 minus is bisulfate, or hydrogen sulfate. So everything else will. All the other weak acids will react and they'll form the weak acid. So which means that this fluoride concentration goes down, Le Chatelier's principle, shift right, more dissolves. So yes, barium fluoride, the answer is yes, it is more soluble in acid than pure water. Is that making sense? So if you're having another hard time thinking about this, so you didn't, maybe, I have a little sister, well, you guys, well, I guess you didn't see her.
So is the hydrogen iodide?
What's that?
Is the hydrogen iodide?
HI, yeah.
Okay.
Well, hydrogen iodide in gas and water, it's hydroiodic acid, if you want to be technical. But yes.
I'm sorry, I'm solving for B.
You're what?
I'm solving for B.
Solve for B? Oh. Is that, okay, that's still working. Okay. I'm just listening to the computer ding at me. If you want to look at it another way, imagine that you have to like fill a box full of cookies, and you're in your kitchen, and you have to keep on cooking cookies until you fill the box. And if you have your hungry sibling in the kitchen with you, what's going to happen? Well, every time you try to fill the box, the sibling's going to eat all the cookies. So you have to keep on making cookies until your sibling gets full, and then you can fill the box. I think that's kind of what's going on here with that, is that you have an equilibrium, and you need to get to a certain value, like filling a box or getting to a KSP. And if there's something in the kitchen or in the solution that consumes your product, you have to keep on going until that consumer is satisfied. So for A, the answer is yes. Okay, so B, for B, so silver iodide, this one here, I minus is from HI, a strong acid. So I minus is from HI, a strong acid. So therefore, I minus does not react with hydrogen ion, and you have no change. So silver iodide is same thing. So silver iodide equilibrium, silver plus plus I minus. But I minus is from HI, a strong acid. So it doesn't bond with hydrogen. It breaks apart. So putting this in acid or water makes absolutely no difference because none of these get consumed. So it'd be like if you're baking cookies and your sibling has like a gluten allergy or something like that. So like, oh, not gonna eat the cookies. I can just fill up the box, no problem. So same thing here, this is not gonna react and no change. So for silver iodide, no. Is that making sense? Okay, so calcium hydroxide. For calcium hydroxide, so question, will calcium plus 2 react with acid? No, it won't. Will hydroxide react with acid? So what, the answer is yes.
Because like, yeah, I can make water.
Yeah. Yeah, H3O plus or H plus. However you want to write the equilibrium. So, if you add acid to calcium hydroxide, this will cause, so to go down and you shift right. So the answer is yes. So here, calcium hydroxide. So if you add calcium hydroxide to acidic solution, it will be more soluble than in a plain water solution. Why? Because the acid will consume the hydroxide, and you'll have shift right, and you have a little more will dissolve. It's the whole idea. So remember that if you decrease the products, you shift right. So it's using Le Chatelier's principle. Okay, so the key with this one is you have to look at the anion, and the general rule is things tend to be more soluble in acid, and the really only exception to that is if the anion does not react with water. I'm sorry, with acid. And the anions that don't react with acid are chloride, bromide, iodide, nitrate, perchlorate, and hydrogen sulfate, or bisulfate, however you want to call the in chemistry class, bi means extra hydrogen. So sulfate is SO4 minus 2, bisulfate is HSO4. Or hydrogen sulfate is the official name. Okay, so questions with this one? So TSP, trisodium phosphate. You can buy this stuff at Home Depot. I have some of it. Makes good laundry detergent, cleaning things. Is it more soluble in acid?
Is it?
And if you have like H3PO4.
Well, not okay, HCl. Good question, though. I like your thinking. How many people think yes? How many people think no?
What do you mean more soluble? Like,
I mean, you can get more
more
dissolved.
more of it in like water versus
Does sodium react with hydrogen, with acid? The sodium ion, does it react with acid? Does the phosphate anion react with acid? Yes. It'll, even one would form HPO4 minus 2. 2 would form H2PO4 minus, and 3 would form H3PO4. So you could react with any number. So reacting with acid will cause the PO4 to increase or decrease. Decrease, because it gets consumed. If it gets consumed, it decreases. And if you decrease a product, do you shift or do you do absolutely nothing? You shift to the right, which means more or less will dissolve. More will dissolve. So is trisodium phosphate, is it more soluble in acid? Yes or no? Yes. Yes, it is. Are you guys following the logic? Do you have any questions with the logic? No questions with the logic. It's science. So, yeah. And there's my other statement. Repeat what I just said. All right. So at the risk of your brains turning off, we've reached the end of the stuff that's testable that I'm going to test you on for the next test. So this is not, you're not being tested on this, but I'm talking about it anyways. Does anybody have any questions about testable stuff before this? Okay. So, precipitation formation. There are certain cases where you can selectively precipitate out ions to purify things. So there is a mineral called dolomite. Dolomite is calcium and magnesium carbonate. Okay? So if you want, you can take dolomite and you can grind it up and then heat it up, and you'll form calcium and magnesium oxide. And then you can throw that into water and you can dissolve a little bit of it. Or I guess maybe you throw it in hydrochloric acid. So you can take that, throw it in hydrochloric acid. I guess you wouldn't even have to burn it then. I guess you take dolomite and throw in hydrochloric acid straight away. And you get calcium and magnesium chloride. So calcium chloride, magnesium chloride. And let's say that you're a raw material supplier and you have a contract with both Tums. No, it's not Tums. Rolaids, sorry. You were a supplier. You're supplying to both Rolaids and to Xerox because they use calcium carbonate to make white paper. Okay, so in your raw material is dolomite, calcium magnesium carbonate, and so you take the dolomite, you throw it in acid, and you get the solution, and then you take that solution and you add sodium hydroxide to it. What will happen is that the magnesium hydroxide will precipitate out first. So you can use precipitation as a way to get rid of selective compounds. So the fact that, looking at the relative size of the KSP, so the difference in that is 10 to the 7, so 10 million. So that means calcium hydroxide is 10 million times as soluble. So it's really easy to separate this out. Just add a little bit of base, and all the magnesium is going to come down. So you take the first amount, and you get really, really pure magnesium hydroxide, which I use to make Rolaids, or milk of magnesia. And then you can take the calcium chloride, and then you can bubble carbon dioxide through that and get really ultra pure calcium carbonate, which what they use for doing things in paper manufacturing. So two different processes, but you can get, using a combined mineral, you can get two really pure products that you can sell to someone else. So that's one of the ways that we do that. So selective precipitation is not precipitation. That's not the typical way of separating things. Anyone want to guess what the most typical way of separating things is? It's how we get whiskey. It's how we get rum. Distillation. Yeah. Yeah, distillation is by far the most common. So used for petroleum. Petroleum, of course, is the highest of it. So there's other types of separation techniques. One is called liquid extraction, or just liquid extraction, which, among other things, is how we mine for gold, at least in the United States. So so we're going to go away from precipitation. We're talking about complex formation. So if you look here, so silver actually complexes with water. Although we write it as silver ions, most ions actually complex with water. And ammonia, if you throw silver in ammonia, you can get a ammoniated complex. And so instead of like when we had KSP and Ka, we always had these really, really tiny numbers. The formation numbers, they're always huge. So it's, in a way, it's kind of fun because like with the acid dissociation constants, they never dissolve. They just like a little tiny bit. And same thing with KSPs. They never really dissolve all that much. Now we got something. Now it's 1.7 times 10 to the 7. So same idea. Products over reactants. So water's a liquid. It's aqueous, so you don't include it. So product, silver ammonia complex, divided by the silver water complex and ammonia squared, and you get a value of 1.7 times 10 to the 7. Huge number. You're probably already familiar, at least slightly familiar with complex formation, because you have the iron thiocyanate. Remember you had that lab view. Did you? I wasn't there. Was it? You could see the orange color, couldn't you? Yeah, that's the complex formation. That's the FeSCN complex. So iron thiocyanate complex. It's orange. That's a fun lab because you can see it. So let's look at some of these, and you might notice some of them. They all have cyanide in them. So, and some of these are huge numbers. So, silver cyanide, 21, 10 to the 21, and silver hydroxide. So that's kind of hydroxide. Doesn't always mix with everything. But look at cadmium. You have cadmium bromide, 10 to the 3rd, cadmium iodide, 10 to the 6th. Then you have cadmium cyanide, 10 to the 18. So it shows you that cyanide's really, really good. And they don't have gold on here. Okay. Oh, but look at mercury cyanide, 10 to the 41. Iron cyanide, 10 to the 35. So this is why cyanide kills you. So if you breathe in cyanide or eat cyanide, inject cyanide, it bonds very, very strongly to the iron in your hemoglobin, which causes suffocation. So same thing with carbonyl, carbon monoxide. Carbon monoxide bonds too. Did you guys talk about that in the back bonding? Did you talk about that in molecular orbital theory? Okay, so Jeff didn't cover that. Okay. I cover it. Yeah. Okay, so let's do an example of this. So, oh, and I told you how we get gold. How we get gold right now, basically, almost all of the gold, this easy gold, is gone in the United States. Meaning, like riverbeds, gold's heavy, so it sinks to the bottom. Riverbeds initially are a great place to find gold because it doesn't react. So, like the heavy mud, like if you just sift through it. So I guess you can do this a little bit, like called panning for gold. You can take muddy water, like especially the water that's deep down, and you can just kind of run water through it and just sift it over and over again. If you do this for a very, very long time, you get little particulates of gold. And it's because gold is heavy, it sits to the bottom and doesn't react. Okay, so now most of that is gone. You can do that in they do this in the Amazon illegally. You can still get the mud, the just kind of sift through and get the kind of the heavy mud, but the gold particles are really small. They do is they dump mercury metal into it, and the mercury metal will suck up the gold, and you get the mercury metal and you hit it with a blowtorch, and then the mercury evaporates and you're left with this kind of spongy looking gold left over. So that's the Amazon River, unfortunately, is polluted with mercury because of that illegal way of doing it. What we do in the United States now, we find places that have a little bit more gold than others, so micro amounts in rocks. And same idea, we grind it up or run water through it, grind it up, and we get this kind of heavy mud. And then we throw cyanide into it, and then we take the cyanide solution, and then I don't know the exact steps, so let's see, I guess you could hit it with acid, that would shoot off cyanide gas. You can then get the gold out of that. But it uses quite a bit, it's a little bit much more involved than simply just going and finding rocks and just start chipping away at the rocks and finding nuggets of gold. Actually, frequently you find gold stuck in quartz veins because of ocean water. Ancient ocean water had much more gold than is in the ocean today. And so quartz veins are where you look for gold, and you can find the gold, and you can just pound it out and get the gold metal out of that. So they call that gold ore, but it's not really gold ore. It's a mixture. Okay, so we do use that, and you can use it to extract other metals too. Not just gold, but gold is the most typical. So let's look at this example. A 200 milliliter sample that has 1.5 times 10 to the minus 3 molar copper nitrate mixed with a 250 milliliter sample that has 0.2 molar ammonia. After the solution reaches equilibrium, how much copper plus 2 remains? So the way that you do this equilibrium is, you know how we've been discounting x's and these kind of things? We're just saying that, so the K formation, 1.7 times 10 to the 13, so that's 17 trillion. It's a big number. Only thing bigger than that is the national debt. But so the idea with that is that we shift all the way to the right. So this initial, I've just taken these numbers here rather than go through and do all the calculations now. That's the concentration of copper, and that's the concentration of ammonia with the mixture. Okay, and in this case, copper is a limiting reagent, and versus ammonia. And here, the copper more or less just gets completely consumed. So we're saying shift right, and we're shifting all the way to the right. And we're even discounting this change for extents of the reaction, just because it's especially with the sig figs, you can't tell the difference there. So the equilibrium then is, so that we went to the equilibrium value. So the formation constant is going to be the product, Cu NH3 4 plus 2, all over concentration of copper plus 2, and then ammonia is the fourth power. So we know what the formation constant is. It is 1.7 times 10 to the 13 equals we know this. This is about 6.7 times 10 to the minus 4, all over our unknown value, and then 0.11 is the fourth. So we can rearrange, we can multiply by 0.11 to the fourth power. Actually, no, that's not the best way to do it. Multiply by x, and then divide by 1.7 times 10 to the 13. So, which means the way we would solve this one, we'd multiply by x, bring that over there, over here, and then we divide by this number, put it over there. That moves x closer. So you can guess this is going to be a small number. So 6.7 e minus 4 divided by 1/4 power. So this equals 2.7 times 10 to the minus 13. So a couple points in here. The concentration of copper is not. Does anybody want to see the calculator on that? Raise your hand. Okay. So a couple points here. The first point, part of the problem, is that we have free copper ions, not complexed, very small, not many at all. 10 to the minus 13, really, really tiny. So the other thing to note, so we're doing these ice charts. We're used to doing small things. And in this case here, for the complex formation, they zoom all the way to the right. So it's almost all completely consumed. So when it comes to these discounting terms, you can discount certain terms by saying it happens all the way to the right, and we're just going to ignore all that stuff. So this reaction here, we just say, you know what, this is all going to go away, and this is going to be ever so close to 0, so we can solve for that. But the rest of the stuff, we're just going to discount and just say it all goes to the right. So that's kind of one of the other things. When you look at the relative values of K, remember we talked about it, and we started studying the equilibrium. That's a big equilibrium constant. 1.7 times 10 to the 13, 17 trillion. That's a big number. It's a really big number. So 17 trillion equals this, which means the reaction really just, there's a whole bunch of this and not a whole lot of that. And then you can make your math shortcuts that way. So it's a combination of mathematical ability and also thinking through the problem, thinking, what does the K mean? What do these numbers mean? And this is another reason why computers can't do chemistry. Only humans can do chemistry right now, because only a human has the ability to make this type of judgment call. So we can't program computers to do this yet. So maybe in the future. But Watson, Siri, and Alexa could not solve this problem. So, okay. And I guess I started talking about this last time. Any questions with this? And as much as I worry saying this, it's not going to be on the test. You know, academia is weird. It's one of the few businesses that students are more satisfied with less. The consumer prefers to have less. Until the consumer is not a student, then the student wants the previous to have more. So, meaning once you graduate, you're like, can't believe kids these days. With their emojis and their brain implants. I didn't have a brain implant when I was in college. Who knows? Who knows what the future holds? Okay, so last topic. Some metal hydroxides can be amphoteric, meaning they'll act like acids and bases. So aluminum hydroxide, for instance, this can sometimes be used in underarm deodorant. So it's the antiperspirant deodorant that frequently contains this stuff. So you can mix it with acid, and it'll react with the acid to form aluminum ion in water. And also at the same time, you can take aluminum hydroxide and react with base to form a complex. So, and of course, as I said before, that the aluminum ion never really sits just by itself in water, it complexes. So water is a fairly strong. Well, actually, it's kind of in the middle. It's a middle complexing. It likes to complex with its whatever's around it. And this is actually something that we're studying now, that we don't entirely understand what happens in solution with the energy-wise. So the water attaching itself to the aluminum, it changes the energy levels of the aluminum +3 electron energy levels. And this also leads to certain types of chemical reactions. In solution, some things happen only in solution. So double and triple bond formation in carbon molecules, I mean, it can form in the gas phase, but it's extremely unlikely to happen. It almost never happens. Only in the liquid phase is this going to happen. Or a solid-liquid interface. That could happen. Or an enzyme in a liquid phase. So that's one way. And that's important to an emerging field called astrobiology. So they're looking to see how is life being created. And if you wonder, like, oh, this planet might have liquid water, like, why do we care that this planet has liquid water? Because certain biomolecules can only be formed in liquid. So things like, so some building blocks would be okay. Like the building blocks for a cell membrane, that could be fine. Maybe even, well, nitrogen bases, they're a little complex. They need to have a little stabilization. So cell membranes could. So maybe there were cell membranes formed, and then inside the cell membrane, the phospholipid bilayers, maybe some chemistry started happening, and then things like DNA and RNA started to form, and then things were passed on. So, but that wouldn't happen in space. You can make alcohol in space. I don't know so they took some pictures of some nebulae, and they said, like, oh, these things, they'll smell like raspberry. So apparently if you go to these nebulae, they'll smell like raspberry booze, whatever that is like. So they see, but of course if you look at the news release on that, it's methanol, it's not ethanol. And you can't drink, well, you can drink methanol, but it'll kill you. Well, you'll go blind. So go blind or die. So, I think I told you that, you know what the cure for methanol poisoning is, don't you? More booze. Just drink lots and lots of alcohol. So we're still studying this. We don't really understand this, and we know that it's important for chemical reactions. We're getting closer, but we know that it's important for the molecules of life. So that's why, if you look in the news, like, oh, liquid water, yay! It's because of maybe life could form. So you're not going to see weird exotic things. At least life as we know it. Life as we know it, the way we are, could only be formed with a liquid interface. But maybe there is a different form of life. I don't know. I guess we'll find out. Okay, so we're done 10 minutes early. Does anybody have any questions about anything? So the next test is, so you have spring break. Next week is spring break. I'm going to go to Wisconsin, but I'm sure you're all jealous. So, yeah, my mother, she has dementia, and I don't know how long she's going to be around, so I try to spend as much time with her as I can. So I'm going to be going to Wisconsin. I'm still technically on duty, although I don't have to be on campus at spring break. So if you guys have any questions you want to ask me, feel free to email me, and I'll get to you eventually, provided that I'm not traveling or doing something, but be a little slower response. But feel free to email if you have any questions. So Monday after spring break, we will have a test review. So we'll go over the previous exam. And then the Wednesday is the next test. And from the brief feedback, the general idea is people want to come in before and stay after the test, right? And if you want to take the test in the testing center, I'm totally fine with that. So if you prefer the learning center to the classroom, it's really whatever. I want you to perform better. You want to perform better. If taking the test, the learning center will make you perform better. Easy. So, if you want to have an anonymous tip to me, feel free to email your peer mentor, and she will let me know. So, Any questions? Okay. So I have the discussion session planned, but you guys are free to go. And there's the optional this problem session, which I will start now then.
Can we review the test?
What?
Do you want them back?
No, you can keep them.
Oh,
Can we review the test?
You want to review the test right
Isn't
now?
that Monday?
Well, that's
Monday's spring break.
Next Monday?
yeah. And next, well, I mean, it's not a very effective use of time because the Monday is prep for the next test. I tell you what. How about we look to the end of the semester? Like if there's time at the end of the semester, I'll do that then. Or we can do it. Or we're gonna do the next problem session. We can look at this. So I'll post the answers. I'll give you the answer key. So okay. So we'll just organic comes in at 4:30. So we've got 20 minutes. I might be able to pop out a few of the questions before we have to run over the astrolab. Well, I guess we can run the astrolab now. Might as well.
Might as well.
Yeah. Okay. All right. So I guess I can stop recording.